Okay, class. So what we're going to do next is talk about the absorption trends of aromatic compounds, infrared spectroscopy. This is following right on the heels of the alkanes, alkenes, and alkynes. So aromatics. So in many ways, they are similar to the alkenes, but there are a couple notable differences. The first major similarity we'll see is that the CH stretch for the aromatic hydrogens comes out, as we said before, just over that boundary of 3,000 wave numbers. So the all those sp2 hybridized carbon stretches are over 3,000 wave numbers. The second issue with those CH bonds is the out of plane bending of those carbons. So just like the benzene molecule of aromatics are of course flat, so those protons can bend up and above and below the plane. And these bends also appear in the fingerprint region of the spectra, and it's extremely useful for determining the ring substitution. So in the example here where we've got a single methyl group associated, bonded to this benzene ring, there's a specific pattern for the monosubstituted when the system's monosubstituted. So we're going to use these two regions exactly like we did with the double bonds. The CH stretch, there's a slight difference here. We've got two carbon-carbon double, like the aromatic carbon-carbon bonds. There's a pair of vibrations, one at 1600 and one at around 1475. So we'll see these here in the spectrum. And the other part, which is going to help us determine, this is the new thing, the substitution pattern on the ring, is there's an overtone region from around 1677, so somewhere around here, to around 2000. And the peaks which appear in the overtone region are typically very weak, but the substitution pattern on these peaks in conjunction with the out of plane bends can help determine this, basically the substituents on your ring. Is it a monosubstituted ring? Is there two substituents, and what's the relationship, etc. So here is a nice visual representation of these, the two regions that you would use together. So the monosubstituted benzenes, of course, will have a strong peak at around 700 and something around 750 wave numbers. Ortho, so the ortho is when the two groups are on the carbons 1 and 2, so side by side. They have a strong absorption at around 750. When the two groups are 1, 3 apart, also known as meta, you will get 3 absorptions, and there's the one at around just under 900 is medium, so sometimes that one's a bit lower, doesn't absorb as strongly. Para substitution, we've got a strong absorption between 800 and 860 or so. Then there's a series of patterns when you've got 3 substituents, which all match as shown. Now, what typically you would do is you would look at the out of plane bends, and you would also try to match it with the overtone region. So the interesting thing here is that the way that this is drawn, it's compressed, so it's sort of squished together. But the monosubstituted tends to have 4 peaks, the ortho 2 strong peaks, the meta 2 peaks, and then this third one's a double peak, so to speak. Para's got 1 prominent peak and a small one. So you would use these in conjunction with that And because the out of plane bends tend to be far stronger absorptions, these, in practice, these seem to be more reliable than the overtones, but because the overtones are quite weak, so they can be obscured by other things. And it says here that depending upon how you do your sample prep, if it's a thin film or it's neat, then these can be easily seen. There's also some functional group reliabilities. So certain groups are quite reliable, other ones are less reliable. So just keep note of that. The last slide is just a couple of examples. So same chemical formula, constitutional isomers, an ortho and a meta compound. You'll see that, again, CH stretches above 3,000. And the things that really change here are the double bonds. This one's quite weak on the ortho. This one's stronger. These two are more aligned. But the main difference, of course, is the substitution pattern. So strong, strong, medium in the case of meta, and then one large, strong one at around 750 or so in the case of ortho. And if you squish the two overtone regions, you'll see that these match quite closely with what we had drawn previously, what we've shown previously. So the meta, 2 peaks and the third one's a double. Ortho, the 2 peaks, 2 strong peaks together. And this matches quite nicely with what we've got. And here's another example. So the para isomer as well, strong out of plane bend at around 800. Overtone matches it. This region is very similar, above 3,000, the sp2 hybridized, and then we've got the aromatic carbon-carbon stretch. And sometimes things which can be a little bit confusing is the if you've got an alkene, we're mixing 2 functional groups here. So with styrene, you've got an alkene which has an out of plane bend, and you've got a aromatic ring which has got an out of plane bend. So the fingerprint region can be quite confusing if you're not careful, I guess. So these 2 peaks here correspond to the monosubstituted ring. These 2 peaks here correspond to the monosubstituted alkene. And there are some additional carbon-carbon stretches there. But I guess the take-home message for aromatics is that much like with alkenes, there's the out of plane bends. You can use the fingerprint region to determine the substitution pattern. Very similar with aromatics. So, and they've got the added little bonus of this overtone region where you can use this to, in conjunction with the out of plane bends, to determine that substitution pattern. All right, excellent. I think that is it for the aromatic section.